Hey everyone, welcome back to Everything is Relative, where today we are going to be looking at some Papa Cambridge topical past paper questions on the topic of quantum physics for Cambridge A-level physics. And the questions I'm going to look at today range from question 338 to 343 as numbered in the Papa Cambridge questions. So I'll leave a link to the website in the description below. You can download these questions. And like always, my suggestion is that you try them on your own before you watch this video to help you with any understanding of the questions that were a little tricky for you. So this is not all of the questions, and these questions are more along the lines of the photoelectric effect. And the next video that I will upload will be the quantum physics questions that are more along the line of line spectra and absorption spectra and so on. So most of these questions are based on the photoelectric effect. And as always, I'll write the questions down since they aren't very clear here. But these are compilations of questions from past exam papers. And these are quite useful when studying and preparing for your final exam. So the first question, number 338, is coming from 9702. That's the subject code, summer 21, which is June 2021. Question paper 4, variant 1. And this is question number 12 from that paper. So if you want to, you can find these individual questions in these individual papers if you want to answer them in isolation. Now this question says, electromagnetic radiation of a single constant frequency is incident on a metal surface, which causes an electron to be emitted. So immediately we think photoelectric effect. They ask us to explain why the maximum kinetic energy of the electron is independent of the intensity of the incident radiation. So we basically want to know, for the photoelectric effect, why kinetic energy of the electrons that are emitted when a photon strikes a metal surface. Remember, if I have a metal, then in comes a photon of light with energy hf, or hc over lambda. If the energy is high enough, out goes an electron, and the electron, if that is, the energy of the photon is greater than the work function energy of the metal, and the electron will be emitted, and the electron has kinetic energy a half m, or the maximum kinetic energy it can have is a half m v max squared. It can actually have a range of kinetic energies. The maximum kinetic energy is independent of the intensity of the incident radiation. We want to explain why. So remember what happens in the photoelectric effect. Firstly, like I said, the incoming photon, or the frequency, I should say the frequency of the incident photon. So I'm going to say the frequency of the incident photon, the photon that is incident on the metal, that strikes the metal, determines its energy. So the energy of the photon depends on its frequency. And the intensity, if you remember what the definition of intensity was, is just giving us an idea of the number of photons that will strike the metal surface at any time. So the intensity is I'm too lazy to write the word number, so I'm going to say NO. You will write the full word for number. It's the number of photons incident on the metal surface per unit time. So it gives us an idea of the number of photons per unit time. Now the kinetic energy of the emitted electrons, or of the ejected electrons, depends only on one thing. So if I have a single electron being emitted, remember for the photoelectric effect, the single electron only depends on the energy of a single photon. In comes a photon, out goes an electron. We can't have a bombardment, an array of a collection of photons giving rise to one electron. That doesn't prove the particulate nature of this effect, of photons specifically. So the kinetic energy of the emitted electron depends on the energy of a single, very important, a single photon. So the reason why the maximum kinetic energy does not depend on the intensity is because the intensity is simply the number of photons per unit time, but the energy of a single photon is going to give rise to a single electron, and so the kinetic energy is independent of the intensity. The number of photons that come in doesn't matter because that energy doesn't gather over time. It's a single photon that must have sufficient energy to eject the electron. And so the frequency of the incident photon determines its energy, and the intensity is simply the number of photons per unit time. And so the kinetic energy of the emitted electron depends on the energy of a single photon. Again, these laws and rules about the photoelectric effect is something that you're going to have to read and understand. And often, like in this case, you're asked to recall them. So now a more calculation-based question that says ultraviolet radiation of wavelength 250 nanometers is incident on the surface of a sheet of zinc. The maximum kinetic energy of the emitted electrons is 1.4 electron volts. Determine in electron volts the energy of a photon of the ultraviolet radiation. So exactly the same effect. In this case, we are told the wavelength of the incoming radiation. Now we know the energy of a single photon, E, is hf. Since we don't know the frequency, but we know the wavelength of the photon, we can write this as hc over lambda, since c is equal to f times lambda. So we can actually write this in terms of the speed of light c and the wavelength of the photon lambda. And h is Planck's constant, which we can just turn to our data sheet and see to three significant figures is 6.63 times 10 to the minus 34 in SI units. And the speed of light, or the speed of an electromagnetic wave, is 3.00 times 10 to the power 8 meters per second. And we now must divide this by the wavelength, which is 250 nanometers, so that's 10 to the minus 9. But this is going to give me an answer in joules, and I can do one better. I can take this entire answer and divide it by 1.6 times 10 to the minus 19. And so I'm going to just multiply this by 1.6 times 10 to the minus 19, and that's joules per electron volt. So I want to convert the answer, which would be in joules, to the electron volt. And what I would find here is that I get 4.97 electron volts, and two significant figures, this would be 5 electron volts. So basically, calculate your answer in joules. Once I have my answer in joules, I then divide it by 1.6 times 10 to the minus 19 joules per electron volt. Remember, the joule is a much smaller unit of measure, hence we use smaller in value. And so what would happen would be I would cancel off the joules and I would be left with an answer in electron volts. And so I'd get an answer here of 5 electron volts. So know how to calculate the energy of a photon in joules, but also know that we generally use electron volts for energies that are this small. You don't want to be writing energies on the order of 10 to the minus 19, 20, 21 joules, etc. The next part asks us to also, in electron volts, determine the work function energy of the zinc. Now, the conservation of energy equation tells us the energy of the incoming photon, which we calculated, hc over lambda, is equal to the kinetic energy of the ejected electrons, half mv squared, plus the work function phi. But we are already told the kinetic energy of the emitted electrons. They've given it to us as 1.4 electron volts. So actually, I can rearrange this equation and solve for the work function of this metal, phi being hc over lambda minus a half mv squared. I didn't really need all the symbols here because all these values are known. So that's 4.97 for the energy of the photon, which we calculated above, minus the kinetic energy given as 1.4, and this will already give us an answer in electron volts. And we should get 3.57 electron volts to two significant figures, 3.6 electron volts. So we really didn't need the use of all these symbols. I could have said energy of photon is equal to kinetic energy, maybe just EK max, plus work function. I could have ignored all the symbols. But that's the conservation of energy equation for the photoelectric effect. And I can rearrange and quickly solve for the work function without any in-depth calculations. And so that question was a nice mix of conceptual understanding and calculation. And as you can see, that was purely based on the photoelectric effect. Now, the next question, you see there is a question that has been repeated, but the next question is question 340, and this is subject code again, physics is 9702, A-level physics, winter, so this is November, December of 2021, question paper 4, variant 2, and this is question number 9 in that paper. And the first thing they ask us is state what is meant by the photoelectric effect. So what is the photoelectric effect? Well, we've been talking about it. It is the emission of electrons, and I'll say from a metal surface, to be more complete, from a metal surface, when electromagnetic radiation is incident on that surface or on it. Now, obviously, you can also say that the electromagnetic radiation must be of a minimum frequency for electrons to be emitted. But this is what the photoelectric effect is. In comes electromagnetic radiation, out goes electrons, provided that the radiation has a sufficient frequency. And the next question for 1 mark says, state what is meant by the work function energy. The work function energy specifically is the minimum, and again, this is stuff that you will remember from doing these things a countless number of times. It is the minimum amount of energy, or the minimum energy required for an electron to leave the surface of the metal. If the incoming photon does not have that amount of energy, the electron doesn't go anywhere. It must have at least the work function energy for the metal if the electron is to leave the surface of the metal. So we must state it's the minimum energy required for an electron to leave the surface of the metal. Now, part B says a polished calcium plate in a vacuum is investigated by illuminating the surface with light. It is found that no photoelectric current is produced when the frequency of the light is less than 6.93 times 10 to the power 14 Hertz. And they want us to state the name of the frequency below which no photoelectric current occurs. Now, we've given this frequency a very special name. It's called the threshold frequency. Any lower than this frequency and the photon does not emit an electron. And so we call this frequency the threshold, the minimum frequency that allows the photoelectric effect to happen. Anything below this, there will be no photoelectric current produced, no photoelectric effect. And you can see even more conceptual questions. They want us to explain how the photon model of electromagnetic radiation accounts for this phenomenon. So basically, how does our idea that light acts as a particle, as a discrete particle of electromagnetic radiation, which is the photon, account for the photoelectric effect? Now, we need to remember exactly what photons are. By definition, photons are discrete packets of energy or discrete quanta of energy. So that's the most important thing to say. Discrete means they can only have a certain value of energy and some multiple of that value of energy, but not a continuous range of values. And what electrons can do, electrons can only absorb or interact one photon. So this means that the electrons must receive all the energy they require from that one photon or they will not move at all. So electrons are only emitted if the photons, so the incoming photon's energy is at least equal to the work function, at least enough to get the electron out of the metal, is at least the work function energy of the metal. So photons are discrete packets of energy, and electrons can only absorb one of these photons, so the photon must have an energy that is significant enough, in this case at least the work function energy of the metal, to be ejected from the metal. And so this is when the photoelectric effect will occur. And so that was a significant amount of thinking, but not a lot of writing eventually for the 3 marks. So if you know your theory, you can answer these questions in a very short space of time. The next question says calculate the work function energy in electron volts of calcium. So let's see what information we are given. We are told that the threshold frequency is 6.93 times 10 to the 14 hertz, and we're actually not given much more. Well, luckily we don't need much more. We know that the work function is Planck's constant h times the threshold frequency f0, the minimum amount of energy for the photon to have, hf0, with the minimum frequency. Minimum energy corresponds to minimum frequency. And so this is 6.63 times 10 to the minus 34 joule seconds, which is Planck's constant, multiplied by the threshold frequency, which we are given to be 6.93 times 10 to the 14 hertz. The answer, remember here, needs to be in electron volts. What I get is 4.59 times 10 to the minus 19 joules. But I want the answer in electron volts. So I'm going to divide this by 1.6 times 10 to the minus 19 joules per electron volt. And you can see I'll get a nice number on the order of 10 to the power 0, on the order of a number that is somewhere between 1 and 10. And that's how I know that I've converted from joules to electron volts correctly, at least in situations where I have a single atom or I have a metal in the use of the photoelectric effect. And so I get 2.87 electron volts, and to 3 significant figures, this is 2.87, doesn't change, 2.87 electron volts. And so that's the work function energy of the calcium metal. Now that question was worth 9 marks, and that was a good mix of, do you understand what the photoelectric effect is, and can you use, well, it wasn't much calculation, but a basic calculation to calculate the work function energy. So you can see questions can be a mix of calculation and understanding of the concept. It's very important that you understand both. What were his conclusions about the photoelectric effect, and how did this impact the particulate nature of the photons, which were previously thought to be waves. Now the next question is question 341 as numbered, and this is 9702. This is from the March exam of 2020, and it's from question paper 4, variant 2, and this is question number 10 from that paper. So the first question says, by reference to the photoelectric effect, explain what is meant by work function energy. Okay, so we've done this already, and this is, I'm going to write it again, the minimum energy required for a photon to remove an electron from the surface of a metal. So I might have used different words, but the idea is the same. It's the minimum energy that a photon must have in order for an electron to be removed from the surface of that metal. And so that's the minimum amount of energy required for the photoelectric effect to occur. Now in part B, we are told that in an experiment, electromagnetic radiation of frequency f is incident on a metal surface. The result in figure 10.1 show the variation with frequency of the maximum kinetic energy Emax of the electrons emitted from the surface. Ooh, so now we have a graph of kinetic energy against frequency. And the first thing we are asked to do is to determine the work function energy in joules of the metal used in the experiment for 2 marks. So how do I find the work function energy? Well, the first thing I like to do when I see a question like this is I always try to write the equation for the photoelectric effect. HF, incoming energy, is equal to the kinetic energy of the ejected electrons plus the energy that goes to the work function to eject the electrons. If I rewrite this equation so that I linearize it, I can see Emax is on the y-axis, so I'm going to write it on the left-hand side. Emax is equal to HF minus phi. Aha. So now I can see how they've plotted this graph. Emax is on the y-axis. The frequency F is on the horizontal axis, the x-axis, which means the gradient of this line, they didn't ask me for it, but it's good to know what I'm dealing with. The gradient is Planck's constant h, and the y-intercept will give me minus the work function. So also usually like to do is extend the graph. Definitely not like that. So we can extend this graph so that at least it cuts the x-axis. Can't seem to get rid of that line, so we'll ignore that line's existence for now. So the graph will cut the x-axis. It's not a very good straight line, but cut the x-axis. Again, you would draw this with a ruler and a pencil, and you can see that the graph cuts the x-axis at about 5.45. Again, it's going to be up to you to make sure that you are drawing this line correctly. So how do we find the work function? So the work function is phi, and we know that phi is h times the threshold frequency, f naught. Do I know the threshold frequency? Well, the threshold frequency is going to be the frequency with the maximum energy of the electrons is equal to 0. So I'm going to have to look at where energy is equal to 0 and see where the graph cuts the x-axis. And it's somewhere where I've placed the x. So that's 6.63 times 10 to the minus 34 Planck's constant times the threshold frequency, which I'm estimating to be about 5.45 times 10 to the 14 hertz. And the answer needs to be in joules, so I can simply write it as is. 3.61 times 10 to the minus 19 joules. What are two significant figures? 3.6 times 10 to the minus 19. So I needed my understanding of the equation as related to the graph to be able to find the x-intercept of this graph and know that the x-intercept will be the threshold frequency when there's no maximum kinetic energy. When there isn't any kinetic energy from the electrons, they're just being kicked out from the metal and they sit at the surface. They don't have any kinetic energy to move away from the surface. And so we can use that little trick to find the work function energy of the metal. But we're not quite done just yet. Next, we are given the work function energy in electron volts for some metals, tungsten, magnesium, and potassium, and we want to determine the metal that is used in the experiment. So what we need to do is figure out what matches most closely to our work function. But didn't we already calculate that? We did, but we calculated it in joules. So we can take our work function, 3.61 times 10 to the minus 19 joules, and convert it to electron volts. That is divided by 1.6 times 10 to the minus 19 joules per electron volt. And this gives us 2.26 electron volts. So that's the work function metal, the work function of our metal, which we can see aligns to potassium. And so my conclusion will be, therefore, the metal that is used in the experiment is potassium. So you had to quickly calculate the work function in electron volts, so convert the work function into electron volts, and then determine which metal it was by looking at the table. Now we are told in the next question that the intensity of the electromagnetic radiation for one particular frequency in B is increased. State and explain the change, if any, in the maximum kinetic energy of the emitted electrons. Okay, so we increase the intensity but keep the frequency the same. What will happen to the maximum kinetic energy of the electrons? So each photon, what happens to each photon? Each photon transfers its energy to only one electron. Remember, we said this before. What's happening to the energy of a single photon? Nothing. We have more photons coming in, but each photon still has the same energy. Now, since the photon frequency, hence the photon energy, does not change, the maximum kinetic energy of the electrons do not change. So the energy of the photons remain the same, and only one photon can excite or eject one electron, so the electrons don't have any more or less kinetic energy. They'll have the same kinetic energy. We just have more of these electrons being produced, which is actually the next part of the question. State and explain the change, if any, in the rate of emission of photoelectrons. Now what we have is more photons arriving per unit time. That's what increase in intensity mean. So they arrive, they strike the metal. Each one of them interacts with an electron. So there's more electrons that will be ejected, and hence the rate of emission of photoelectrons also increases. So more photoelectrons, or rather I should just say more electrons. We know them to be photoelectrons. More electrons are emitted, and obviously the rate increases. So per unit time, more electrons are emitted. You can say, to be more concise, per unit time, and the rate increases. Rate meaning how many are being emitted per unit time. So it's in the stating already. So the rate of emission of photoelectrons also increases because the number of photons coming in increases, and so the number of electrons going out increases. And that was a 7-mark question. So that was a good mix also of, do you understand what happens if I change any of the variables? And again, I can go back to Einstein's conclusions about the photoelectric effect if I'm ever confused as to what I think will happen. Now the next question is question number 342, and this is 9702 from summer of 2019, which is May, June 2019. Question paper 4, variant 3, and question number 11 from that paper. And the first question expects a deep understanding of the photoelectric effect. It asks us to state 3 pieces of evidence provided by the photoelectric effect for a particular nature of electromagnetic radiation. Now, luckily for us, there's more than 3 answers. So there's more options for us to remember this and hopefully get it right. So the first one I want to talk about is the maximum energy of emitted electrons, the maximum kinetic energy of emitted electrons depends on the frequency of incident radiation. It does not depend on the number of photons that are coming per unit time. If this was a wave nature, this wouldn't happen. the maximum energy of the emitted electrons wouldn't really depend on the frequency. It'll just depend on how much of total energy is coming in from those photons. Get enough energy in, and then the electrons coming out will get enough energy. But it doesn't happen this way. And so that's proof that photons are behaving in a particle way when this happens. Another piece of evidence is the existence of a threshold frequency, which tells us that one photon is interacting with one electron. So below the threshold frequency, no electron emission can occur. Now, if light was a wave, if this was a wave behavior, if this occurrence or this phenomenon was because of the wave nature of the photons, then it doesn't matter what the frequency of the photons were. Eventually, with time, the energy would stack up and the electrons would be ejected. But this tells us that each photon is interacting with an individual electron like particles do, and hence the frequency needs to be a certain value. The energy needs to be a certain value before electron emission can occur. Waves can accumulate energy over time, but photons require the energy to be exactly the same as the electron requires before the electron is ejected. And amongst the others that you can write, I'm going to say that electrons are emitted instantaneously. Again, if this was a wave effect, I think it's spelled correctly. Electrons are emitted instantaneously. If this was a wave effect, we would expect that the energy would build over time, be transferred to the metal, be transferred to the electrons, and then the electrons would be ejected. But this happens immediately. In comes photon, out goes electron in a very short space of time. And so you can also talk about the intensity, not the frequency, the kinetic energy of the emitted electrons not being dependent on the intensity, which again wouldn't be the case for a wave behavior, and the others that you will find in your textbook, as Einstein mentioned. So 3 pieces of evidence that show that the photoelectric effect proves the particulate nature of electromagnetic radiation. Very important thing to know. It's something you shouldn't ignore as you're studying the photoelectric effect. We are then given the work function energies of some metals in the table, and each of these metals is irradiated with electromagnetic radiation of wavelength 380 nanometers. They ask us to calculate the energy of a photon that has a wavelength of 380 nanometers. Again, this we can do in our sleep, but we have to calculate in EV, so there's a bit of conversion to be done. E is hc over lambda. Planck's constant is 6.63 times 10 to the minus 34 times the speed of the electromagnetic wave, 3 times 10 to the 8 meters per second. All of these values will be in your data sheet. And I need to divide this by the wavelength, which is given. 380 times 10 to the minus 9 meters. What I get is an answer, again in joules, 5.23. And you can see the similarity between this question and ones that we've done in the past. So there's some overlap. So I get 5.23 times 10 to the minus 19 joules, but they expect the answer to be in electron volts. So I need to divide this by 1.6 times 10 to the minus 19 joules per electron volt. And I should get 3.27 electron volts. Now, quick check to see if my calculation makes sense. 3.3 electron volts is to compare it with the work function energies in the table. If it's something of a high or low power of 10, I can assume that I've done something wrong in the calculation. And we are then told to determine which metals will give rise to the emission of photoelectrons. So how do I know? I'm told the energy of the wavelength of light that's going in to strike the metal, and I'm given the work function energy of different metals. Well, what I need is that for this photon energy, the one that's actually going to be striking the metal, to be greater than the work function energy, else no electrons will be emitted. So I require that the photon energy be greater than or equal to the work function energy for that metal. And I can see immediately by looking at my answers that 3.3 electron volts is bigger than 2.4, bigger than 2.9, but smaller than 3.6 and smaller than 4.3. So it will happen, it will give rise to the photoelectric effect or the emission of photoelectrons for sodium and calcium. And so my two metals that will allow the photoelectric effect at this wavelength, which is ultraviolet light, is sodium and calcium. And these are the ones we use more often in the lab to demonstrate the photoelectric effect, because we can use light of frequencies that are ultraviolet or even violet and blue to demonstrate the photoelectric effect. And so we can use our knowledge of what does the work function energy mean to determine which metals will be able to undergo the photoelectric effect. The last part of the question says photons of wavelength 380 nanometers, which is the wavelength we used above, are incident normally on a metal surface at a rate of 7.6 times 10 to the 14 every second. All the photons are absorbed in the surface and no photoelectrons are emitted. And we want to know the force exerted on the metal surface by the incident photons. Now this might be a bit troublesome because we don't know an equation for force when it comes to photons. In fact, it's weird because photons are these massless things, but they actually are applying a force to a metal. And it is possible. Photons can be used as things that can move sails and can actually move objects. They don't have a lot of energy to them, but they can physically push stuff. So what do I do? Well, I'm going to first turn to de Broglie's wavelength. And I'm going to say lambda is equal to h over p. And actually not de Broglie's wavelength, because that's confusing. De Broglie's wavelength are for particles, but these are photons. So what do I remember about, I'm going to have to bring in another concept before I even get to force, and that is momentum. The momentum of a photon is E by c, the energy of the photon divided by c, which is hc over lambda times 1 over c. So the momentum of a photon, the equation is analogous, but it isn't de Broglie's wavelength. The momentum of a photon is h over lambda, Planck's constant over the wavelength of the photon. And this is for a single photon. So one photon has this momentum. But why would I calculate momentum? Because I know that force is the rate of change of momentum, delta p by delta t. Aha. So what this means is it is the momentum of the photon over the time, h over lambda t. And this is 6.63 times 10 to the minus 34. Again, this is for a single photon, divided by the wavelength, which we are told is 380 times 10 to the minus 9. And I'm going to assume that the time is 1 second, because they told us that the photons are incident at a rate of 7.6 times 10 to the 14 every second. So I'm going to use a time of 1 second to get the force exerted in that second. Now this is the force exerted by one photon. But what if I want the total force? Because I now have 7.6 times 10 to the 14 photons. So I take this force and I multiply it. I take 6.63 times 10 to the minus 34 divided by 380 times 10 to the minus 9, and I multiply it by the number of photons that are striking the metal. 7.6 times 10 to the power 14 of them every second. And what I get is 1.326 times 10 to the minus 12 newtons. Or to two significant figures, 1.3 times 10 to the minus 12 newtons. This is a tiny amount of force, but it's a force nonetheless. It's insignificant, but it's not zero. So photons can actually push things, can actually physically exert a force on something. If this something was in space, where there were no resistive forces, these photons could be used to actually move an object through space. Again, a lot of photons have to strike a metal just for a tiny force, but when there's no resistive force, a little does go a long way. So it's possible that photons can exert a force on an object even though we say they are massless. And that's because they carry momentum. They carry the ability to push objects, basically. And so that question was 11 marks, quite a long question and quite confusing. You had to first find the momentum before you could go further to find the force. When you get a question that asks you for a force exerted by a stream of photons, immediately try to think about the momentum. That'll help you at least get further in solving that problem. The next question is question 343, and this is subject code 9702. This is from winter 2019, so November, December 2019, question paper 4, variant 1, and this is question number 11 from that paper. And the first question says, with reference to the photoelectric effect, state what is meant by the work function energy. So again, we've mentioned it before and we have mentioned it in terms of the photoelectric effect. So we'll do it again. We can never get bored of this. The minimum energy required by a photon to remove an electron from the surface of a metal. So that's specifically talking about the photoelectric effect, because that is the photoelectric effect. When an electron is removed from the surface of a metal by a photon that has an energy that is at least the work function energy. So that we'll never forget. We'll keep doing it until we memorize it. Next, we are told that the work function energy of a clean metal surface is 5.5 times 10 to the minus 19 joules. Electromagnetic radiation of wavelength 280 nanometers is incident on the metal surface, and the metal is in a vacuum. We are told to calculate the photon energy. Again, we could close both our eyes and still be able to do this. E is hc over lambda, which is Planck's constant 6.63 times 10 to the minus 34 times 3 times 10 to the power 8, and the wavelength in this case is 280 nanometers, which is 10 to the minus 9 meters. We have to convert it to meters, which gives me an energy which they want in joules anyway, lucky for me, 7.1 times 10 to the minus 19 joules. I'll keep that to two significant figures, 7.1 times 10 to the minus 19. We are then asked to calculate the maximum speed of the electrons that are emitted from the surface. So I'm going to have to write the photoelectric equation out. HF, incoming photon, is equal to 1/2 times the mass of the electrons times the maximum speed squared, which is the kinetic energy of the electrons, plus the term for the work function energy. Which means I can rearrange this and solve for the maximum speed as being a little bit of algebra. I prefer doing my algebra first before putting in my values, but that's completely up to you. This is the square root of 2 into HF minus phi. I hope the math is mathing, divided by m, which is, if I put in my values now, I get this to be the square root of 2 into, now the energy of the photon is 7.1, minus the work function energy is given as 5.5. Both have the same power of 10. It's minus 5.5 multiplied by 10 to the minus 19, since they have the same power of 10, divided by the mass. Now be careful, this is the mass of an electron. Don't use a single atomic mass unit. An electron is much smaller, 9.11 times 10 to the minus 31. It's the electron that's being ejected. What I get is 5.93 times 10 to the power 5 meters per second. So a significant speed, 5.9 times 10 to the power 5 meters per second. And so that's how we could manipulate the photoelectric equation to rearrange and solve for the speed of the electrons. Actually, it wasn't anything difficult, it's just a little bit of mathematics. It may have taken you more steps to do it than I have. It doesn't matter. Make sure you get it right. Next, we are told to explain why most of the emitted electrons will have a speed lower than Vmax. So there's a reason why there's Vmax and not just V. Why will some of the electrons, or many of the electrons, have a speed lower than the maximum speed? Now remember that more energy than the work function is required to bring electrons to the surface. The work function is the minimum amount of energy. But some electrons require more energy because they are deeper in the surface of the metal. They undergo more collisions and hence they require more energy to get them out to the surface. So the work function is only the minimum amount of energy, the electrons that are easiest to get to the surface. So in general, more energy than the work function energy is required to bring the electrons to the surface of the metal. So just be careful, the work function is called the minimum energy for a reason. Most electrons require much more energy. So if you really want to have the full effect of the photoelectric effect, you need to have energy that is higher than the work function. So more energy than the work function energy is usually required to bring electrons to the surface of the metal. And so they'll have less energy to be given to kinetic and hence a lower speed when they are ejected. Now the last part of the question is a little bit tricky, and we are told that the electromagnetic radiation incident on the metal surface may change in intensity or in frequency. And we are told to complete the figure below by inserting either increases, decreases, or no change to describe the effects of the changes shown on the maximum speed and on the rate of emission of electrons. Wow, okay. So we are given a certain change, and we want to know how that change affects firstly the maximum speed of the electrons and the rate of emission of electrons. And the first change is reducing the intensity at constant frequency, and the second change is increasing the frequency at a constant intensity. Okay, so quite a lot of information being given there. Let's first see how changing anything affects anything else. Now what I know is that the maximum speed of the ejected electrons depends purely on frequency, not on intensity. And so if I increase the frequency, I definitely increase the energy of the electrons emitted. And the intensity, or the maximum speed, does not depend on intensity. There's no relationship between intensity and speed. Just the number of emitted electrons will increase when the intensity goes up. So intensity is proportional to the rate of emission, the rate of electrons being emitted from the surface. So the intensity is proportional to the emission rate, provided that we have a constant frequency. Okay, so let's start this table and see how far we can get. So if I reduce the intensity and I keep the frequency the same, what happens to the speed of the electrons? Nothing. Each electron gets its energy from each photon. The energy of each photon remains constant, and so the kinetic energy of the emitted electrons faces no change. What about the rate at which the electrons are being emitted? Well, I have the same energy of photons, but I have less of them. So I have less electrons being emitted, and so the rate of electron emission decreases. So far, so good. Next, I want to know what happens to the speed of the electrons, the kinetic energy of the electrons, if I increase the frequency, but I keep the intensity constant. Well, I'm giving each photon more energy, hence I give more energy to each electron. And so yes, they'll have a higher kinetic energy and hence a higher speed. So the maximum speed of the ejected electrons will increase. Now the last one is a bit tricky. What happens to the rate of emission of electrons? The frequency is increased, but the intensity stays the same. Now you may think that there'll be, well, no change. Constant intensity means constant rate of emission. But it's not completely true. So now if we want to keep the intensity constant, so we are told that the intensity is remaining constant, right? So if we want to keep the intensity constant, intensity by definition is the power per unit area. Now if you remember from way back when you studied waves, power per unit area. Power is energy per unit time. So we can actually think of this as the energy per unit area per unit time. Now, if I increase the frequency, what am I doing? I'm increasing the energy. Up goes the energy when I increase the frequency. But I'm saying that the intensity must remain the same. So if the area over which the photons are striking the metal surface is not changing, then the time must increase as well. So if I want the same energy, I must increase the time as well, which means if the time goes up, the rate decreases. So I'm getting the same number of photons, but I'm now getting them at a larger amount of time. So since I'm taking a longer time to get the same photons onto the metal, the rate at which the electrons are leaving also decreases because it's taking a longer amount of time for the same amount of electrons to be ejected. And so the rate of emission of electrons actually decreases. So just be very wary of this. It's not that just because the intensity remains constant that the rate of electrons that are being emitted remains constant as well. It actually decreases. You should find some explanation of this in any good textbook or any good set of notes, but I hope this clears it up. So they were easy 3 marks, but the fourth one was a little tricky. Still, the other 3 were not too difficult to determine if you understood the concepts behind the photoelectric effect. So the next time I make a video, I'll probably do more questions on quantum physics, but more of those based on the line and absorption spectra, and maybe the de Broglie wavelength and other aspects of quantum physics, such as energy levels in atoms, that we didn't really cover in this video. And that's because the questions are structured in such a way that those questions come later on in the topic. So I hope this video was helpful. Please leave a like if it was, leave a comment to tell me if there's any other content you'd like to see on the channel, subscribe, share this video, and I'll see you again next time on Everything is Relative.